I wanted to say first, good morning to all, and thanks for coming. And thanks for coming to this last seminar of this HeartTree-FOCA Spring Open seminar sessions. And today I'm very grateful to Dr. Alex Hamilton from the UK, who was working at the CAQ almost 10 years ago. We remember a few minutes ago when we had that time the Consolidator big research project. Yeah. And well, now Alex will tell us a bit about his latest chemistry and also the other part of the job, which is teaching at the university, right? And well, thanks again, Alex, yeah, for accepting this invitation. The session will be recorded since Alex gave his permission. So then we'll have a round of questions, and then we'll stop recording and can stay and can keep chatting a bit more if you wish. So Alex, thank you very much, and so happy to see you again.
Excellent, thank you, Carlos. So I'll just share my screen, make sure I share the right one. Excellent. Excellent. So hopefully everyone can see the title page. So it's like, once again, thanks, Carlos, for the invite to come along and to reconnect with the ICIQ community. As I said, it was a very informative and very useful and very enjoyable aspect of my postdoc time, and definitely helped kind of where I've ended up and being able to pursue a career within academia. So as I say, we've met most people now, but for people who joined a little bit later, I'm Dr. Alex Hamilton. I'm a physical chemist, Department of Biosciences and Chemistry at Sheffield Hallam University. So just as a quick introduction, so I've been at Sheffield Hallam now since 2014. And prior to that, I was a postdoctoral teaching fellow at Massey University, and this is probably what led me down the more teaching route over the predominant research direction. However, as you'll see from the discussion today, research is still very much a large part of what I try and do. So spent a little bit of time, prior to that, I spent a little bit of time traveling across the globe because it makes a nice change. And then, yes, that was then prior the 2-year stay in Carlos's group, where we did predominantly transition metal homogeneous catalysis, but also some organocatalysis too, and led to a few very nice papers. I had my PhD from the University of Bristol with Jeremy Harvey and Guy Orpen. Some of you may well have heard of Jeremy Harvey. And then prior to that, I had my undergraduate degree in Swansea. So I'm now senior lecturer in physical chemistry and computational chemistry, and have research links to the biomolecular sciences research department at Sheffield Hallam, but I'm definitely on the more of the molecular rather than the bio side of that title. So one of my general overarching research interests, as you know, it's probably not, people would have probably guessed, it's within the area of computational chemistry, predominantly within sort of standard DFT, but also looking at sort of some linear scaling couple cluster methods, and also moving beyond to sort of more post-wave function analysis, so QTAME methods, NCI, and I'll talk a little bit about some of those today. Some recent work, and it was really interesting to see what you guys are up to a little bit there around the use of kind of metadynamics to study those kind of gaps in the knowledge that traditional DFT methods sometimes leave. So the areas where these methods are applied to, predominantly reaction mechanisms in homogeneous catalysis, and this is what I'm going to talk about mainly today. But I'm also interested in sort of non-covalent interactions with species because that's inherently important within sort of reaction mechanisms, but there's also a lot of fundamental chemistry we can understand from there. And then also have a sort of a sideline in some time-dependent DFT for luminescent complexes, so sort of functional switchable materials and switchable complexes, and also a recent collaboration with the Defence University of the UK looking at analysis of illicit substrates. So that's kind of overarching of what I do from my research side of things. And then the plan for today, I was going to talk about just one of the areas that my research group look into. So it's, as the title said, it's the synthesis of N-heterocyclic compounds using homogeneous catalysis. And then depending on how the time is looking, I thought it might be interesting to talk just very briefly about actually what it's like to work as a lecturer at a teaching focused university, because you know, you've probably sat through a lot of seminars from a lot of very prominent scientists at some at very big universities who probably don't do a lot of teaching, but that's not the reality of a lot of people who end up in academia. So I thought it could be an opportunity to see a little bit more about what that's the realities of the role. But more importantly, and probably more interestingly for most people, let's talk a little bit about some of the research that, so we're going to talk about one published study from the group that came out last year, and then we'll talk about another unpublished study which one of my master's students has just recently finished up that will hopefully be looking more towards publication in the not too distant future. So the first question is always, why N-heterocycles? Okay, so why are we interested in making cyclic compounds, and why are we interested in making nitrogen-based heterocyclic compounds? So here we've got just a figure of all the small drug molecules which were approved by the FDA in 2019. And although you may not be able to see that clearly, if you look, and the astute amongst you might realize that actually only 3 of them don't contain an N-heterocyclic moiety of one form or another. So clearly it's of an interesting target from a pharmaceutical perspective. And this is not new information, this is not new knowledge, and the mechanisms behind forming some of the simpler N-heterocycles are well known, with an amount, but probably not as much as you would imagine, sort of mechanistic understanding behind how the reactions occur. So myself and Chris, who's very kindly joined us today, we had a kind of review article out earlier this year, looking predominantly at cobalt catalyzed formation of N-heterocycles. I'm not going to talk about cobalt today, but that's a nice read just to get an overview of what the field looks like. So we have some basis for mechanistic understanding to start off with, but there is a lot of scope and opportunity for new cyclic systems, fused heterocyclic systems, all of these leading to potential new drug moieties. So there is a lot of application for what we're trying to synthesize. So what's out there, kind of the basis of the literature, kind of where it all starts off. So we can think of quite simple systems. So part A, we've got at the top here. So we've got this kind of benzamide moiety, which is really very common in a lot of kind of cobalt catalysis and CH activation catalysis. We've got our directing group, which can also act as our part of our substrate of interest that we're trying to form. And so the standard kind of intermolecular interactions, intermolecular migratory insertions of our alkyne into our benzamide substrate. This has been sort of well known since about 2010, give or take. And then so we want to be able to build on from there. And there was a lot of work looking at this kind of tethered. So this is other people's work. This is the background literature, just to clarify. So then people started tethering on our alkyne group, or in this case, sorry, the alkene group, onto our benzamide structure to try and form fused heterocycles. So in this case, sort of benzofurans and tricyclic systems. And then further on from there, we can look, and people have looked at sort of other various using different catalysts and substituting, having different substituent groups within the tethered arm to form a variety of different complexes and different molecules. So where we came in, so this is, as you can see from the slide, most of this is based on sort of rhodium, cobalt, ruthenium catalysis. We published a paper in 2020 looking at some copper catalysis to form along similar lines, but forming a more complex fused N-heterocyclic system. So our dihydrobenzofurane isoquinolanes, and this was a novel moiety in the literature. And in all honesty, it actually came out of a student not listening to the instructions that were given as part of the experimental work, misheard which catalyst or which change to the reaction conditions to put in there, and swapped out the cobalt, which was being tried at the time, for a copper acetate, as we'll see in a moment, and it led to some very interesting results. So, as I say, this came out in Organic Chemical Frontiers in just last year. So, well, the reaction conditions were a little bit of experimental, and if I miss anything out, Chris will kill me, but he can fill us in at a later date if needs be. So we have our kind of benzamide with our quinolone directing group substrate with our tethered alkyne arm, and we are looking at some copper acetate as our main catalyst. It's in a reasonably heavy catalytic loading, but we'll see why that is when we look at the mechanism in a moment. And we also have, and it's important to note, this addition of this additive into the system, which we'll see why that was important as well. And so we have our benzamide substrate forming our fused heterocyclic system. And from the experimental work, it was shown that there is quite a very functional tolerant group, so we can change the R group within our substrate, and we get quite a nice range of different products formed, and we get reasonably good yields for most things that were looked at. So it's a fairly tolerant system, which is really nice, and as is always good to see, a crystal structure was able to be identified of the product formed, which actually showed some quite interesting structural observations. So highlighted on the crystal structure here is just some of the bond angles around our fused heterocyclic system, just to highlight quite how strained this heterocycle actually is, which means there's scope for it to go on for further functionalization afterwards. And it's also interesting to note that through the 2D NMR that was taken on the structure, the orientation, the conformation of our aminoquinoline group actually has the potential for some switchable properties. Right? So it's predominantly in one of the orientations, and there's a scope for looking further into using sort of this structural moiety as for switchable properties by altering the molecule and being able to force the other conformation of our ring. Not something we've looked into with any great detail as of yet, but this could be scope for a potential future work. So just wanting to highlight this, the additive within here, because we'll make note of that on mechanism in just a moment. So we've gone from our benzamide with our direction group, and we've got our formation of our tricyclic fused heterocycle. So how does this reaction work? Because as is kind of normal working in our field, the experimentalist comes with the problem and needs us to figure out what they're actually up to in the lab. So what were they up to in the lab? Let's have a look. So we have our catalytic cycle as we've solved. So this is just sort of standard straight DFT, so it's a PBEO throughout the whole system. So we have the formation. So there was previous work looking at a related structure with the copper catalyst. That's for the deprotonation, the NH deprotonation step to form our catalytic structure. And we had a very low barrier for this step, so we kind of started from our catalyst. We can then undergo our CH activation step and to attack our CH, which is kind of underneath the copper, if you will, through a kind of traditional kind of looking CH activation step, forming this tricyclic substrate, as tri-ligated complex here. So we've got a tridentate of our direction group around our copper center, and we've got our acetate group Deacetate can then be lost, and the vacant coordination site can be filled by the tethered alkyne, putting it in the right orientation for our migratory insertion into our copper-carbon interaction. So the copper-carbon interaction has, the migratory insertion step has a reasonably high barrier, it's a 20 kcal barrier, but this is where the addition of our additive was identified to be able to lower the reaction, and this agreed really nicely with the experimental results. I'm sure I'll be corrected if I'm wrong, but without the manganese additive, the reaction happens, but at a lower amount, it's about 30% yield, but with the manganese acetate, it was closer to a 70% yield. And it was actually really nice to be able to see this. These additives are often used within catalytic systems, but maybe not understood about what they're actually doing as often as they should be. So it was really nice to be able to include this within our understanding of the mechanism. So once we've undergone the migratory insertion step, we can get a structural rearrangement to form our nice stable reactive intermediate. And you can kind of starting to see, so we've got our furan ring that has been formed, and you can start to see where our the formation of our product and how it's working here. So from intermediate E, there's a couple of different processes which could occur, and what we found to be the lowest in energy is a sort of disproportionation step to oxidize our catalyst from copper 2 to copper 3. And this kind of accounts for why there needs to be this 20% of our catalyst, 20% mole of our catalyst within the system. We need quite a high catalyst loading because of this disproportionation step within our mechanism. And then that, from our copper 3 species, we can undergo reductive elimination to release our product and gives our copper 1 species, which can then go on for further oxidation back up to copper 2 and undergo and close our catalytic cycle. So, well, this is, you know, you would expect or would question, does it have to undergo this disproportionation reaction? So do you have to oxidize our catalyst first before reducing it? So we looked at the alternative mechanisms for this to see, just to confirm what our findings were showing. So if we just do this, looking at a standard copper 2 to copper 0 reductive elimination step, both with and without explicit solvent, the barriers are significantly higher in energy. And then we have our kind of oxidation of our catalyst at the end of that process. So these kind of barriers are kind of best part of 10 kcal per mole higher in energy than on the previous slide, which, so we're fairly confident, we are very confident, and the reviewers were more than happy that that was the process by which was this reaction was occurring, which is nice. We then went on to have a look at, so obviously this is the intramolecular kind of migratory insertion, and what would the barriers, what would the reaction look like for an intermolecular alkyne addition pathway, so trying to look the same chemistry, but with an external alkyne coming in rather than the tethered alkyne, because we weren't able to observe any of the experimental work and experimentally observe our reaction. And we can understand that again from our DFT calculations. We undergo a very similar reaction profile, but however, because we've got a substitution of our acetate and our alkyne rather than an entropically favorable just pure loss of the alkyne, our entire barrier heights just shift up by that kind of 15 kcal per mole, which is associated with an entropic contribution. And so we've looked at this with a couple of different alkynes to try and get an idea of what's happening. So that's nice to see that this reaction it works very nicely for the tethered alkyne, and we can understand the whole process of the reductive elimination step, and also explain some of the negative experimental results as well. Just that really confirms our reaction and what's occurring. So we then went on a little bit further to look at some non-covalent interaction analysis and some ketame analysis. So with our initial complex structure, there's two different conformations which which were stable, we have this kind of, on the very left, we have this very closed structure where our tethered alkyne arm is kind of very much sitting underneath our metal center, or we have this very open structure where our tethered alkyne is kind of is pointing out sideways. And if I looked at those before undertaking this project, I probably would have said that the second of those two structures is energetically more stable. There's going to be less steric clashing on the go, would be what I would thought process would have taken me down, and I would have been wrong, it turns out. So as we sort of showed on the initial, on the mechanism slide, it's this kind of closed conformation with this interaction of our tethered alkynes of sitting underneath the rest of our catalyst, which is about 2.5 kcal per mole more stable than the very open structure. So we utilized non-covalent interaction analysis and QTAIN to try and understand, well, why this is the case. So here we've got some reduced density gradient isosurface plots, and then the related kind of scatter plots. So we've got the reduced density gradient on the y-axis, and it's a function of the electron density on the x-axis. But what this kind of tells us is a type of non-covalent interactions which are present within the species. So we've got this kind of gap line down the middle of the scatter plot. Anything to the left of that is energetically favorable. So we've got sort of van der Waals interactions occurring first and some hydrogen bonding. And then anything to the right is more repulsive steric interactions. And so if we compare the two scatter plots, what we see that is, although we do get maybe more steric interactions with the favored structure, which is, as you would predict from looking at them, there's clearly stronger and more prominent sort of hydrogen bonding and van der Waals interactions comparative to the more open structure. So that kind of gives us some idea about why there would be this kind of 2.5 kcal per mole energy difference between the two conformers. And then we can look at the line critical points from the QTAIN analysis to try and identify which of these interactions are what are leading to the stabilization. And so they're kind of numbered in the diagram here and then in our table below. So you can see that the main prominent interaction is this kind of agostic interaction between our copper and the hydrogen that it's going to be interacting with, and that's kind of the predominant stabilizing interaction there. We have a few additional ones. We have the same proton interacting with the alkyne. We have a very weak kind of hydrogen bond between the acetate and our CH2 group of our tethered alkyne. And then there's a little bit of kind of van der Waals. I wouldn't go as far as calling it pi stacking, but some van der Waals interactions between our ring structures as well. And so we've got some of the QTAIN parameters there kind of showing the density and the nature of those type of interactions. However, one of the issues with this whole system really, and this whole chemistry behind this, is this aminoquinoline directing group really limits the functionality of the chemistry. We can vary the R group on our alkyne, and as you saw from experimental, that had very good functional group tolerance. But if you look at most of the benzamide literature, you can also functionalize that amine position as well. But with an aminoquinoline group attached on there, that's going to be very difficult to do while maintaining the directing group properties of the substrate. So what we wanted to do was try and transfer this chemistry onto a more classical sort of rhodium CP star system to remove the need for this aminoquinoline directing group, which would hopefully lead to the same product, but with a greater range of functionalization, so greater access to chemical space. And so this is what some unpublished work that my master's student has just recently been finishing up. And turns out in a nutshell, no, not directly, it's not going to happen, but other interesting things do happen. Okay, so what we found was that we can actually form or lead towards a double annulation process where we have an intra and an intermolecular annulation reaction possible, forming a different fused heterocyclic system now. So now we're forming a dihydrobenzofuran isoquinoline structural moiety, as we show at the end here. So conscious of time, so I'll move through Josh's results reasonably promptly. So I'll just open up. Whoop, I'll go right to the I hit the wrong button there. I apologize. I'm going to have to skip back very quickly. There we go. Sorry, I hit the end button rather than the sideways button. Okay, so the reaction proceeds kind of as you'd imagine. We have our CH activation step, loss of the acetate, and then formation of the alkyne group, allowing for the migratory insertions coming into that vacant site to allow for migratory insertion. And then that's where the complication starts. So there's a variety of different routes which are then possible. But the important one to follow is the black line. So what occurs is protonation of our alkene from an incoming acetate group, which then allows our substrate to isomerize to open up the other CH group on our what was originally the benzamide substrate for a second insertion reaction to occur, really widening the chemical space of our system. So we've kind of covered our bases with all different possible reaction steps which could be leading, but as you say, if we follow the black line, it's the most favored. So then we're able to undergo a second CH activation step on our substrate, insertion now of of a secondary alkyne into our ring system, which leads to kind of our migratory insertion through reaction, and then we lead on to deprotonation of our methoxy group on our benzamide structure, so oxidation up to a rhodium-5 species, which can then undergo reductive elimination and regeneration of our catalyst, leading to our well, we hope to be observed product at the end, which is good. So to further the study and to kind of direct the experimental group, we computationally looked at the tolerance of our alkyne. So we looked at a range of disubstituted alkynes in the second half of that mechanism. So we got a range of kind of electronic and steric properties in there, as well as mixed alkynes as well, non-symmetric alkynes and some push-pull alkynes, to kind of try and understand the steric and electronic factors which are controlling or directing the chemistry of that secondary alkyne insertion step. And as we can kind of see from the table here, so this is just for that alkyne insertion, we get quite a range in our activation energy of that particular step. And it's clear that sort of direct electron withdrawing groups, small electron withdrawing groups are energetically favorable, and large bulky groups and electron donating groups are unfavorable for that reaction. So that should hopefully help direct some of the experimental work to focus their efforts. Continued on to look at some of these non-covalent interaction plots for some of these examples. And you can see these are not overly clear, but you can see, so this, the one on the right is our tert-butyl, and you can really see lots of steric interactions there, some clashing. So these red areas of these isosurface plots show sort of really unfavorable steric clashing. So you can see that these big bulky groups are just not able to insert into our substrate. And then wanting to try and explore some of the selectivity of our non-symmetric alkynes. So here we've got just a range of our non-symmetric alkynes, and this is looking at the product of that reaction step to try and identify if we're going to see any selectivity, are we going to get any selectivity within the products that we observe. And I think the overarching from here is that there is a couple of examples which probably aren't going to work. So what we have, we have our substrate, we have all of our different alkynes, some different than non-symmetric alkynes. And then if we have the kind of the energy difference between the orientation of which they can insert, and as you see, so for some of them, the energy difference is quite dramatic, so up to sort of 10 to 15 kcal per mole. So it's very unlikely that we would observe that as a product of the reaction. So there are definitely some selectivity potentials within this. So it's nice, which is good to see. And then as a final thing, and this is very much analysis in progress, is the application of, in this case, big data ideas to little data. So we've only got 27 different alkynes that we've looked at, but the student had a little, had a go at doing some cluster analysis to try and see if we can observe any particular groupings or any interesting trends within, within the data. So we've got the series of descriptors that they use. So we've got some QTAME topology descriptors, and then some kind of generic kind of quantum descriptors. And there's no, say, atomistic labeling descriptors that went into this. There's no, you know, number of carbon atoms, number of non-carbon atoms. It is all purely sort of quantum descriptors in there. And the main thing we see is that we do get this kind of grouping of our kind of electronically neutral, if you will, alkynes to the one side, which splits off quite early within our cluster. And shall we say, analysis is in progress on this to see quite how many trends we can dig out from this. My theory is with only 27 ligands, probably not a huge amount, but it's interesting to see what the data looks like. Excellent. So just to kind of, that concludes that aspect of it. And given the time, maybe we won't do too much on the teaching side of things, but to mainly just include that, rather than concluding on the specific science, just to say really there is a lot of chemical space which is still unexplored, and it's our job as computational chemists and chemists in general to try and find out ways of accessing it. As I mentioned, sometimes mistakes from students and researchers isn't always a bad thing, because it can lead to quite some interesting results. And as I say, reactions don't always go to, as you would first imagine they might, don't always go to plan, but this can lead to some interesting findings, as the two different projects we've talked about have highlighted. So as I say, that's just sort of one aspect, and maybe the more interesting aspect of my role. But working as a teaching university, a couple of things to bear in mind if you do end up going down this route. There is a lot of teaching, as anyone will, I'm sure Chris will back me up on this, at least half to 2/3 of your time are taking up with teaching and the administration which goes behind it. So which makes time something very, very precious. One thing I've definitely found from my role is that we have many hands, but not much kit. So all the work that's been presented today and all the work that I've published over the last 5 to 7 years is all done on individual workstations. I don't have access to a computing cluster. So it just shows that what you can do with limited resources. However, I'd much rather have the resources that you guys have access to. And yeah, choose your collaborations wisely. So I'd just like to make some final acknowledgements. So this is my current research group, although most of the students are just finished up because they're a mixture of masters and BSc students. So Josh up here, he did he did all of the rhodium work that we talked about just now. Ryan's just started in my group as a PhD student looking at some of the CO2 work that you may have seen at a recent RSC conference. And Jacob, some of you may have met from a few years ago. So he's working on some kind of nanocomposite molecular dynamics over with our engineering group. And also, I think Chris, who's here with us this morning, and he's obviously the experimental powerhouse behind bringing all of these problems. And as promised, here's the youngest member of my research group, and you can't start them off too young. So excellent. Thank you ever so much. That basically concludes the thing I wanted to discuss this morning. Does anyone have any questions with regards to the projects?
Of course. Thank you, Alex. Right. Great talk. Thank you very much, and very nice chemistry. Extremely complex reactions. Yeah.
Yes, particularly that rhodium one just kept on going on and on and on.
Yeah. Yeah. Complexity increases. Yeah. But it's really great to perform calculations before experiments. So
yeah, so it will be very interesting to see if our predictions of selectivity are correct. I wait with bated breath to be told no, they're not. But you know, it's the nature of it.
It will. DFT works.
Nice.
Yeah, so I open the session for questions. If anyone wants to ask some question to Alex, some comment, just switch on your mics or switch on the camera. Well, if not, I start by a question or a couple of comments. Yeah, I like it. We also use this NCI function to visualize, the non-bonding interactions. And it's really interesting. And I don't know if you have realized that in some cases the shapes that we observe as those interactions are quite curious. Haven't you ever observed rings, kinds of rings of kind of curious shapes, I would say.
As in like the trajectory of the line critical points, you mean? And where the curvature within those, or?
Yeah. So the isosurfaces of the
okay, yes. Yeah, I guess it's because the isosurfaces they predict on, I guess if you change your value of your isosurface, you can get even stranger shapes or reduces because obviously they're predicted along line critical points, which is why you maybe get, you saw some, although I went through it quite fast, sort of if you've got the rhodium with a CP star, you always get that very negative space, right, as a ring structure around it.
No, I just was wondering that if it would be worth to try to classify interactions according to the shapes of that function. I don't know. I think it's curious, but maybe it will require a special project to follow up that.
Yeah.
But also,
they are going to be very system specific as well, mind you. So how digging out some generality from that would be interesting to do, definitely.
And then so this function, so analyzing this kind of interactions means that you need to reproduce the electron density in these almost void regions quite precisely.
Yeah.
And I think that I saw that you are using a very large basis set. Is precisely this is the question, or?
Yeah. So for the basis set for the energetics for so actually, the two different basis sets for each different project. So there was a triple Zeta basis set, and then with the rhodium stuff, we had the second polarization function in there as well. To be honest with you, I've not really looked at specifically myself the the effect of the basis set on the Q-tame analysis and how much it really does vary. So I've seen a few talks by various different groups where they see that it's reasonably generalized. So there, I think, once you get into the triple Zeta basis sets, there isn't actually much variation within the analysis that you get from the Q-tame results. And also there's not really a huge variation between DFT functional and even looking at things like CAS FCF calculations. It's all quite stable, which is nice. It shows that the methods work well. Yeah. So no, I'm a big fan. As you can see, most of the work published over the last few years has had a little bit in there. I think it's as you say, it's nice to be able to visualize your results in more than just here's an energy surface. Thank you very much. So
good, thank you. More questions, comments?
Hello,
Stefano.
Yes. Oh. Hi, Alex. Thanks for the talk. It was very nice, interesting. I'm not really an expert of the sector, so it's just more of a curiosity. I think in the first mechanism you showed, there was the copper changing oxidation state and ending up in as copper 2, I think.
So it starts off as copper 2 for most of it.
Okay, yeah, and it ends up as copper 1.
And then then there was a disproportionation reaction. So you oxidize it up to copper-3 to then undergo reductive elimination, to favor the reductive elimination step to form copper-1.
Okay, yeah. So my question is, do you have some idea of how to regenerate the catalyst, so to recuperate the oxidation state?
So to go from the copper-1 back up to the copper-2, start the catalyst cycle over again. Yeah. So in the paper, it was commented on that, you know, there is oxygen available in the system to undergo this step. We didn't really look at it explicitly. There would also be the case of we've got a lot of catalyst in there. So we've got a lot more, you know, there could well be another syn-proportionation reaction, because with 20 molar percent catalyst, there's a lot to play with. So undergo it. So that could be kind of self-regenerating in that form as well. Yeah, so that was based. So we didn't explicitly look at it from the calculations, but it definitely does occur.
Okay, thanks.
More questions? I have a question. So about teaching, when you say a lot of teaching, what does a lot means?
So a lot of teaching, I would imagine during term time, I probably average, I say face-to-face, but that concept has changed these days, somewhere between 12 to 15 hours a week. And then that's obviously administration and meetings and on top of that. So officially, I think my contract is 20% research, which is August.
Yeah, same as here in Spain. No? So normally teaching at the university requires a lot of dedication, and not only time face-to-face in the classroom, but also then at home maybe grading and preparing and grading. Yeah, it's.
But I mean, I think what goes along with that though is some level of job security compared to, say, if your job is dependent on getting in the next big research grant that everybody else is going for. There's a lot more job security in a teaching role than there is in a purely research role in the UK, at least. I have friends who are very good researchers at very good universities, but once they're not getting in £500,000 a year in research grants, they haven't got a job.
Yeah.
It swings and roundabouts a little bit on that front. I think I'd rather have the job security and the big teaching load.
And on the other hand, teaching is it's lovely job. I love teaching. Yeah, but yeah, when this makes you stress, then yeah, you can complain, but not that much. Okay, if there is no any other question or comment, maybe you can stop recording.